people from the same institute. So it's going to start.
Okay, good. So, thanks for the people who stayed. So, we were asked to review supersymmetry breaking in realistic model building in string theory, in older string theory, which of course is a huge topic with really a lot of work done on it, and there's no way that practically one could cover actually all the work done on it. So apologies if I miss some important work on the subject, and if I miss some references to important work on the subject. So this is, a kind of a partial view on the subject. So first of all, let me define what we'll actually talk about in this review. So realistic model building in string theory must incorporate a number of things, realistic particle physics being one of them, but also modular stabilization, cosmological constant, inflation, and so on and so on. And in this talk, I will limit to the particle physics model building side to make it a more manageable task, of course. So just to define that. And if we're going to think about supersymmetry breaking, I guess the nice thing is that we have a very well-defined starting point with string theory, and that is that realistic model building in string theory must incorporate supersymmetry at some scale, at or below the string scale, in order to accommodate target space fermions, in the sense that target space fermions require world-sheet supersymmetry, and then following some mild assumptions on the stability of the vacuum, you end up with target space supersymmetry. So at least we know from string theory supersymmetry should be around at some scale, so that's a good starting point. Of course, the breaking of supersymmetry depends on many things, and a wide spectrum of properties of the particular compactification that you're doing, and therefore I think, as our current understanding of the subject is, it's very hard to give some universal description of supersymmetry breaking in string theory or in model building, and therefore, in this review we'll have to adopt the approach that we'll have to look at different approaches, the different string theories to different approaches to model building, and how supersymmetry breaking is realized in each of these different approaches. So that's what we'll do. So here's the very quick plan. So I'll start to talk about type 2B model building, and then Timo will come on and talk about some F-theory model building, global aspects of F-theory model building, and a quick introduction to F-theory model building. And then I'll come back and talk about F-theory model building from a local approach. And then Timo will come back again and talk about heterotic model building and M-theory and type 2A model building.
And then you conclude together.
And then we will conclude together and in synchronized. Good. So in each case, we'll try to briefly review the model building, the implementation of supersymmetry breaking, and we were asked to talk about open problems and challenges, so we'll try and do that as well. So I hope that's okay. So I start with type 2B model building. I think this is a good place to start because, I think in my opinion, the interaction between particle physics model building and supersymmetry breaking is probably best understood in this setting, and that is because we have good control over modular stabilization, which is a prerequisite to understanding supersymmetry breaking. And there's in some sense two generic sources of supersymmetry breaking in these kind of approaches to these models. So there is the universal, as far as I understand, component of supersymmetry breaking, which is the uplift. So in all these models you stabilize in ADS, so you have to uplift, and that will break supersymmetry. And in the large volume scenario, supersymmetry is broken already in the ADS vacuum. So these are two sources of supersymmetry breaking that appear in these compactifications. And so, let me start with the most general configuration in the large volume scenario. Perhaps the most naive thing you would guess and start to try. And if one does this, then the general answer for the gravitational mass. One can calculate the gravitational mass in this. So supersymmetry is broken already in the vacuum, and one finds that it's basically given by the Planck scale over the volume of the manifold. And the gaugino and scalar masses are roughly given by a similar quantity, the Planck scale over the volume times the log of the volume. So this is the basically punchline for the supersymmetry breaking scale in this vacuum of the large volume for the most generic case. And this means that if you want TV scale supersymmetry, if you want the gravitational mass to be around a TV scale, you have to take the volume very large, and it implies that the string scale must be the intermediate scale. The string scale basically lies halfway between the gravitational mass and the Planck scale. And okay, this may be considered a challenge perhaps to these models, because perhaps intermediate ski scale depends if you like it or not. It could be a challenge, or it could be a nice property. But what is a challenge, I think, in this scenario is that typically there is a cosmological moduli problem in such cases, unless you can find some fancy mechanism to solve it, in the sense that you see these scalar masses are basically around the gravitational mass, and the same would be for all the moduli. So you'll have many moduli sitting around a TV scale, plus you'll have the modulus associated to the large volume, to the volume of the whole space, which is even less than all these masses, so it'll be even lighter than the TV scale. So this is certainly, I think, a challenge for this most basic generic scenario. But something that emerged, so I think the next big step perhaps in understanding supersymmetry breaking in these models emerged from thinking about the possibility that the F term for the Kähler moduli that appear in the gauge kinetic function of the visible sector could vanish. And why would we think that could be the case? Well, there is this could arise due to the tension between moduli stabilization and preserving the gauge symmetry of the standard model, in the following sense that instantons in the superpotential that involve these moduli that appear in the gauge kinetic function of the visible sector may, I say may because there are some subtle ways to get around it, but generically will be charged under some visible sector, under some visible sector, not U1s, visible sector gauge symmetries, and this can lead, they'll be charged under some U1s that the visible sector matter fields are also charged under, and this means that if you have e to the minus t in the superpotential, this will only be gauge invariant if you dress the instanton with a prefactor which involves matter fields that are charged under the standard model gauge symmetries. So these matter fields are charged under this U1s, but also under the standard model gauge symmetries. And this means that for this term to be non-vanishing in the superpotential, those matter fields would have to get a VEV, and they would break the standard model gauge symmetries. So that is the general argument, up to some subtleties, which I won't go into, that it's possible to get around this. Why we may expect that the fields that appear in the gauge kinetic function for the visible sector, the Kähler moduli, will not appear in the superpotential, and it turns out if they don't appear in the superpotential, then the F term vanishes, because the piece of the F term that's the first piece, which is the derivative of superpotential, vanishes, and the piece that's proportional to the derivative of the Kähler potential is proportional to the D term associated to them, which also vanishes. And in the case where the F term vanishes for the Kähler moduli that appear in the gauge kinetic function for the visible sector, then such a scenario is called a so-called sequestered scenario, and I'll come back to that in a couple of slides. So if you like, this is the generic scenario, this is a sequestered scenario. So what about the model building? Well, on the particle physics side, de-Broglie singularities provide promising models. Actually, I'll only talk about de-Broglie singularity model building in a type 2b. Of course, you can build also in a geometric regime, but I think the F-theory discussion on that would cover that in a more general framework. So what we do understand in type 2b, which we don't really understand that well in F-theory, is how to do model building in branes of singularities, so I'll discuss about that. So there are, in principle, I think, a very rich set of possibilities for branes of singularities, models you can construct branes of singularities. So I won't be able to cover all the possibilities, and let's not even cover all possibilities that give you realistic models. but let me just give some example, a cutting-edge example. So this is a local example in the sense that it's an example constructed on some singularity without embedding the singularity in the compact Calabi-Yau. So this is some example based on a DP3 singularity. And this is the spectrum, so just to give you an idea of the kind of spectrums that you get, So I think this has some kind of some universal features that one finds in these models when you do model building in brane singularities. One is that you get, well, one is very nice, which is that you get the 3 generations of the standard model. In fact, I think there's some result that you can at most get 3 generations, at least for orbifold singularities, and that's quite interesting. Anyway, so you can get the 3 generations, but typically you get many Higgses. In this case, you get six Higgses, and also in this case, you get an extra U1 symmetry. So, so I think this is a typical challenge. There are multiple Higgs fields in these constructions. I think this is somehow universal in all the models, realistic models based on brane singularities. And of course, if you have multiple Higgses, then one has to work hard to make sure there's no flavor changing currents that are forbidden generated by them, because of course their VEVs would have to be aligned, otherwise you'd get flavor changing currents. So one way, of course, to get around this is that one Higgs gets a very big VEV and all the other Higgses don't get a VEV or a very small VEV, so that the mixing is very small, but one of course would have to engineer that. And this extra U1 symmetry, well, I think it was proposed in these models to get rid of it by giving a VEV to the neutrinos. So if you give a neutrino a VEV, of course you break B minus L, so this would break the combination of these U1 symmetries to the hypercharge. Of course, if you give a neutrino a VEV, then you also generate R parity violating operators. So I guess another challenge, if you want to get rid of the U1s in this way, is how to make sure that they're small enough to avoid constraints. And, well, just a brief flash of flavor physics. It is possible to do flavor physics in these models, and you can get some realistic CKM matrices and masses, things for the quarks. Although, well, another challenge here, I suppose, is that I think it's fair to say that typically these flavor models, they are generated, these masses will be generated by giving VEVs to fields living at the singularity, so in some sense deforming the singularity. Typically these flavor models, though, have many free parameters, so there are many such fields, and you choose their VEVs essentially by hand. So for example, in the quark sector there are 14 parameters to explain 18 observables, which is okay, it explains them, but it's not ideal. I mean, ideally we would like to get many more parameters out than what we put in. So that's, I guess, another challenge, I guess, to get nice predictive flavor models from these models. And I think another thing that's quite generic is that the largest generation typically remain massless, and they would require some non-perturbative effects to generate their mass. Okay, so that's a quick overview of the kind of cutting edge, the state-of-the-art of model building for brane singularities. That was a local model. Here is a global model. This is part of this collaboration's multiple papers, I mean, semi-heroic papers, I think, in really putting everything together. So this is a model based on a DP0 singularity, so this is the quiver for it. And, well, you get, it's not quite the standard model gauge group to start off with. It has 2 SU2, it's a left-right symmetric group. But you can then break it to the standard model by giving some fields appropriate, some fields, some VEVs. And this is the picture. Actually, we saw this in Sven's talk yesterday, I think. So this is where the visible sector lives, and this is the Noye-Interfold action, and then you have all these other things. Again, the matter spectrum is quite good, and then typically, I think, in my opinion, perhaps the most serious issues are multiple Higgses, which seem to be generic for such models. Okay, so the gauge kinetic function in such models looks like this. It has the dilaton in it, and then has some Kähler moduli, or if you like, twisted modes appearing in it. And if we're in a sequestered scenario, as I defined it in the previous slides, that means that there's no F terms for the Kähler fields that appear in the gauge kinetic function, so there's no F terms for these twisted modes, and therefore gravity-mediated gaugino masses, for example, would have to come just from the F term from the dilaton, and one can calculate what that is, and okay, this is what you get. And the interesting property is that you get that the gaugino masses are proportional to the gravitino mass, as one would expect, but there is an extra factor of the volume here, 1 over volume. So in fact, there is a suppression by the volume of the Calabi-Yau more than one would expect from a naive estimation. where you would expect them to be essentially lie around gravitational mass. So that's, I think, and it turns out that that was the gravity mediation. Also, if you calculate the anomaly mediated neutrino masses, there is also the same cancellation. And in fact, this holds generally for the other soft masses. So this is a table of the soft masses that you get in such cases, in sequestered cases for these models. So, and you see that they're all lying around the gravitino mass scale, which sets the scale for these things, up to some, okay, these are log volume factors, but they have this psi squared piece, which is essentially the ratio of the string scale to the Planck scale, or if you like, the volume of the manifold. So they're all suppressed by essentially factors of the string scale over the Planck scale, more than you would naively guess, I think, by just the gravitino mass. And this is interesting because it generates a hierarchy between the gravitino mass and the soft terms for the visible sector. So one thing it allows for example, is the possibility of gauge mediation with a higher than expected gravitino mass. So even if gravity mass is quite high, the soft terms will still be so small from this gravity-mediated contribution that it could be that gauge-mediated soft terms would actually still dominate them. And I think one thing that's quite nice is it allows for a possible solution to the cosmological moduli problem, because the moduli fields will have masses set by the gravitino mass scale. So that means that if you take the gravitino mass quite big, 10 TeV or 100 TeV, then you move up all the moduli with it, so they're quite heavy, so there's no cosmological moduli problem. But you keep the soft terms for the visible sector still quite low. So I think that's a nice possibility for such models, a nice a feature of such models.
What is the comment about the anomaly mediation, which is
so if you so here the gravity mediation would just be for the gaugino is just the F term for these fields, so that would be it. But then you also get an anomaly mediated contribution, and then it's less obvious to see why that would also vanish. At least at the leading term would also vanish, but it just happens that that's the case. I don't know if there's any deep intuition as to why that's so.
surprising, no? Because in general, anomaly mediation is almost the same.
It's surprising, but I think when you do the calculation, that's what happens. I have no insight as to a deep reason why that's the case.
There's something special about no scale that I'm not sure what it is. I mean, anomaly mediation cancels for no scale, but I don't know what.
Oh. But this was this Bagger-Moroi company.
Yeah, that's the formula, but kind of why it cancels, I don't know.
Yeah. If you put it into the formula, it cancels, but. Okay, so that's very nice. That's a nice feature scenario. So let me just talk about some challenges. Because the soft terms are so suppressed compared to the scale of supersymmetry breaking in the bulk to the gravitino mass, this means that corrections to this vacuum, so for example, higher order alpha prime corrections, or as I said in the first slide, the universal contribution to supersymmetry breaking that comes from the uplifting mechanism, may in fact dominate these soft terms in the visible sector. So before, in the non-sequestered scenario, the soft terms were really dominated by the gravity-mediated contribution, but now because the gravity-mediated contribution is so suppressed, it could be that various things that you add to the compaction, for example the uplifting, may correct your result significantly, and this therefore introduces a degree of uncertainty in how to reliably calculate the soft masses in such models, because you then really need to understand things like the uplifting mechanism and things like this. So I think that's a challenge for such models. And well, something we've had to talk about in this conference is it could be that this sequestering is broken by superpotential effects. I think that's something that's currently under investigation. And then something that's not really related to supersymmetry breaking, but let me just make a thing of it, that I think something that's quite nice about these scenarios in type 2b is that the large volume scenarios is that they are really actually strongly interacting with current experiments and experimental data, because typically you actually get a lot of dark radiation in these models, because the volume modulus is light. It begins to oscillate late in the history of the universe. It will reheat the universe, and it will decay typically to its axial superpartner. And so I think something to watch out for is that I think as it currently stands, dark limits on dark radiation are such that with some playing around with parameters, one can still meet experimental things, but as this experimental data gets better and better, it may be that one has to play, in order to make these models consistent with it, one has to play with parameters so much that they become less believable. So it may be that these models will be, in some sense, ruled out by experimental data over the next few years, which I think would be very nice. At least, unless somebody can think of some mechanism to save them, which probably someone will. Yeah. Anyway, so this is a very nice, I just put it because it's a nice example of string phenomenology in the sense that models that are being studied actively in the field are really interacting with contemporary experimental results, so things that will happen in the next months and years. So let it not be said that this is never the case. Okay, so let me just, before I hand over to Timo, talk about some more, I think in America say left field ideas, or some more Baroque ideas. I mean, for me, I think something that's really would be very nice would be to understand supersymmetry breaking directly in string theory. So from a worldsheet perspective, I think this would be fantastic. And of course, especially if if nature has chosen to break supersymmetry at the string scale, which it may well have, then it will be a necessary thing to understand. And I think this is a very interesting thing to think about. It's very hard. There are just a couple of results within the type-2B arena that I'd like to just highlight. One is that there is some calculation of some non-supersymmetric, so anomaly-mediated gaugino masses that are induced by non-supersymmetric flux, done from a worldsheet perspective. So in this case, you take two gauginos and you calculate this, well, one-loop open string, or if you like, tree-level closed string amplitude with a vertex operator for the supersymmetry breaking flux inserted on it. So, which includes also the Ramon flux. So, and one can then calculate the gaugino masses which are induced by anomaly mediation. So I think that's quite nice. And I'll just mention something else. So this is type 1, so, but it's, type 1 is close to type 2b, so I'll mention it here, so-called brain supersymmetry breaking. So this is, I think, an older paper, but I think a very nice result. It's a configuration in string theory, in type 1 string theory, where we can actually understand everything fully in string theory, which actually contains anti-branes. So it contains anti-D9 branes, and supersymmetry is then broken by this anti-branes at the string scale. And yet, it was shown that this configuration contains no tachyons, at least classically. So this is a configuration where, at least classically, supersymmetry is broken at the string scale. You can calculate everything in string theory, and there's no tachyons. It's stable, at least classically. So I think that's something nice. So I think perhaps this supersymmetry break-in from the worldsheet is something interesting to think about for string theories, especially if the LHC doesn't find anything. And of course, the question is, these are done in very simple configurations. Can these be applied to realistic models? And now I hand over to Timo. Okay.
Thank you. So the next topic we'd like to discuss is type 2B model building, not at singularities, but with extended branes, extended 7 branes. And nowadays, the language to describe this is F-theory, because this comprises both the perturbative models and goes significantly beyond that. However, before we then discuss supersymmetry breaking in this regime of non-zero volume 7 branes, we first have to develop the technology for model building in the first place. So we first have to, in particular, make sure that the technology of F-theory is at the same level as in the well-developed frameworks of type 2B, of type 2A, or of heterotic theory. So we need to be able to decide what is wishful thinking in F-theory model building and what actually exists, or as we learned yesterday in Gonzalo's talk, we have to distinguish F-theory compactifications versus F-theory compactifictions. So we need to know what can really be done. And this is particularly important because the field started off purely locally, which is one of the virtues of type 2B models, or also of F-theory models, that certain facts or certain model building ingredients can be discussed locally. But of course, at some stage, one has to be concrete and see if those mechanisms really work. And there were surprises indeed, that some things that were proposed locally turned out not to work, or at least were more complicated. So in order to understand the technology for model building, we need to understand both the technology for particle physics model building and also the technology for modular stabilization, then SUSY breaking, which should be the actual topic. And oftentimes these go hand in hand. For example, one of the main themes of the past few years in this F-theory research was trying to understand better the structure of U1 symmetries. Now, this might seem like a boring topic, but in fact it is at the heart of model building. As we will briefly review, U1s are really crucial in order to get anything close to a realistic model, at least a realistic gut model. And at the same time, as we heard, for example, in Sven's talk, the associated D-terms with U1 symmetries can play a role in certain uplifting mechanisms, possibly in the only uplifting mechanisms that, that might exist or not. So they play a crucial role, and we need to understand how this works also in F-theory. The same is true, for example, for another important ingredient into model building, non-perturbative effects, M5 instantons, which are known, of course, to play a crucial role for modular stabilization, F-terms, SUSY breaking, but also yield contributions to Yukawa couplings, for example, to get close to realistic flavor structure for the Yukawa couplings work by Marchesano et al. Make heavy use of these M5 instantons, and they need to be understood. And I won't say anything in this short review about this topic, but a little bit more about that. So this just as a motivation that we really need to take the time and go back one step and develop technology. It's worthwhile. So F-theory in principle is just a generalization of type 2B, so one could do all the type 2B model building also in F-theory, but in particular one can also do more, namely one can do F-theory gut model building. So in other words, build a UV completion of the standard model, which is an agreement with unification of the forces at some gut scale. And the name of the game would then be to try and address typical challenges of phenomenological or field theoretic gut models with stringy methods or with F-theoretic methods. We'd like to provide a rationale or reason for observed patterns, and as was also stated, I think, yesterday in the discussion session, one of the goals of string phenomenology is to understand and explain hierarchies which might look obscure from a field theory perspective, and this is certainly one of the goals to achieve in these types of models. The two ingredients from F-theory, as you know, are on the one hand the localization of gauge degrees of freedom, which at least can help us accommodate this little hierarchy between the gut and the Planck scale, and the appearance of exceptional symmetry groups, which makes it similar to heterotic string theory, which is important to get Yukawa couplings and the right flavor structure. And complementary to these local model building effects, once more, there has been a lot of ongoing progress in understanding global aspects of the geometry of elliptically fibered fourfolds, of four-form fluxes, which are crucial in order to get the chiral and also the non-chiral matter spectrum, and of effective actions. So just very briefly, the idea of localization of gauge degrees of freedom in type 2B or F-theory more generally. Gravity, of course, propagates in the bulk, whereas the gauge degrees of freedom localize on the 4-cycle wrapped by our 7 branes, where those intersect along a curve. We have charged matter, and the Yukawa couplings then are localized at points of the intersection of those curves. So this gives us here a number of geometric structures to accommodate various scales. In particular, the Planck scale, of course, is sensitive to the volume, whereas the gut scale is sensitive to the volume of the entire Calabi-Yau, whereas the gut scale is sensitive to the volume of the 4-cycle wrapped by the 7 brane, and the gut coupling likewise. So we have now here 3 ingredients: the volume of the 4-cycle of the Calabi-Yau and the string scale, in order to accommodate those 3 physical quantities. And if one plugs in the values, one gets a small hierarchy of this type. The gut brane cycle has to be relatively small, so just a factor of 10 or so, bigger in typical radius than the string scale, and also the Calabi-Yau is not too big, in fact. So all of this can, of course, and is done in type 2B as well. As we said, in order to get Yukawa couplings, we need to go to the non-perturbative regime and describe things in terms of F-theory compactifications, where we replace the notion of 7 branes along devices by the notion of an elliptic fibration, elliptically fibered fourfold. The fiber is just an auxiliary tool to take into account the dynamics of the exodilaton, which is sourced by the 7 branes. And this gives rise to this well-known dictionary between type 2b and F-theory. In particular, once again, the 7 branes are in one-to-one correspondence with the codimension 1 singular fibers. And these geometries can also tell us something about D-1 incident corrections, as are computed, for example, by Billow, Lerda, and collaborators. So the nice thing about this construction is not only that the location of the 7 branes is encoded in the geometry and the singularity of the fibers, but also the type of gauge groups and gauge symmetry is encoded geometrically. Namely, the statement is that the singularity type of the fiber in codimension 1 is in one-to-one correspondence with the gauge group along the 7 branes. To see this, one analyzes not the singular fourfold as such, but the so-called resolved one. So one replaces the singularity in the fiber over, say, the gut brane by a bunch of P1s, which intersect and whose intersection structure then mimics the affine-Dynkin diagram of an ADE group and its generalizations. So the gauge symmetry is directly encoded in the structure of the fiber in these small resolutions. In particular, each of the P1s that we paste in order to resolve our singularity, each of those P1s corresponds to the node of the affine-Dynkin diagram of the corresponding gauge group. And M2 branes wrapping along those P1s then correspond to the off-diagonal elements of the corresponding ADE gauge groups. Or in type 2b language, we get open strings stretching here between the endpoints, so to speak, of these various P1s, which then in M-theory would be fattened to M2 branes. So in order to make contact then with gut model building, we need to ensure that our fibration has a structure of that type, where over some divisor in the base, the fibration shows, say, an SU5, so an A4 singularity, whose resolution then looks like this. However, this is not the only story. So this is the first prediction now of F-theory, that a simple picture of this type never occurs. So whenever you try to get an SU5 singularity in the fiber, you not only get an SU5 brane, but in addition, you have extra branes, extra singularity loci. So this is just a 7-brane tadpole cancellation. And these extra branes, one could call them flavor branes from a 2B perspective, automatically give rise to extra matter. Namely, when these extra components of the discriminant, i.e. the locus where these singularities sit, when these extra components intersect the gut brane on a curve, the singularity structure in the fiber becomes worse. So the resolution has to implement even more P1s, which means that we have more M2 brane degrees of freedom that can wrap those. Those M2 brane degrees of freedom are localized at this enhancement, so over this curve where this gut brane intersects the remaining flavor branes, and this is how we get localization of matter states. In particular, for this simple example of an SU5, generically the following two enhancements occur, namely either from SU5 to SU6 as far as the singularity structure is concerned. Then from the affine-Dynkin diagram of SU6, one get an adjoint with an additional 5 plus 5 bar from the SU5 perspective. So these could be the 5 bar matter or the Higgs fields, the 5 Higgs fields in gut language. And if we have an enhancement to an SO10, this is where the 10 plus 10 bar representation can reside, which then contain the standard model in this fashion. Neutrinos, right-hand neutrinos, on the other hand, do not occur in this picture on the gut brane. These are explicitly non-local effects that happen away from the gut brane. This is also related to the appearance of U1 symmetries. We'll come back to this in a second. Still, all of this could also be done in type 2b. What is now the actually only new ingredient of F-theory as far as SU5 gut model building is concerned is that certain Yukawas, which are perturbatively absent in type 2b, are allowed. Though, namely, we need two types of Yukawas for gut models, the 10 5 by matter 5 by Higgs and the 10 10 5 Higgs. They occur at intersections of the various matter curves. The first one is possible also in 2b, The second one requires exceptional singularity structure in the fiber and is absent perturbatively. The reason why it is there in F-theory is because the branes are actually of different types. These are PQ branes. The open strings here are actually PQ strings, so it's a completely different construction than in type 2B. So the first thing, of course, that we need to do is to understand the geometry of those elliptic fibrations in detail in order to understand how to get this very basic structure, just the gauge group and the meta curves. Of course, there has been tremendous work in the 90s on elliptic fibrations in 8 and 6 dimensions, 8 and 6 dimensional F-theory compactifications. More work in 4 dimensions then kicked in after F-theory was discovered, so to speak, rediscovered in 2008 as an interesting arena for model building. So, for example, one can construct torically resolved such SU5 fourfolds and study them. Particularly exciting is the study of analytic resolutions in higher codimensions, so over the curves and the points, because it is here that where new surprises appear, which were not anticipated just from studying, say, 8-dimensional F-theory compactifications in the 90s. And this has been done very systematically in recent papers by Sakura and collaborators, and also others. So this is a typical structure of how the fibration can look like. In codimension 1, we have the affine linking diagram of our SU5. Then we have these two types of curves, the 10 and the 5 curve. Some of these P1s would split up, as indicated here, and give, in this case, the affine linking diagram, but more general things can happen. Affine linking diagrams of higher singularity structures. And then finally, over the Yukawa points, even more curve splits up, so that all of the structure can be read off directly from the geometry. So here is again the picture. This would now be our gut brain with the SU5 generically, and over certain curves like the 10 curve and the 5 curve, we have these enhanced singularity structures. Okay, so this is very well understood. The message is elliptic fourfolds are at this level well under control, which is something that was not the case like 4 years or 5 years ago. So this is really nice progress. Now we need, of course, to look more into the detail and address challenges of, say, SU5 gut theories, which are hard to address from a field theory perspective. These are, or include rather, SU5 gut model building, SU5 gut breaking, doublet-triplet splitting, proton decay, and then, of course, getting a detailed flavor structure, mu terms, hierarchies, all of this. And basically all of those, or most of those topics, rely on two principal model building ideas in F-theory, which are old, which were proposed 5 years ago already by Beasley, Heckman, Waffer, and Donagi, Weinhold, but whose implementation is really only now really understood, and part of which is still not understood. So one is the gut model, the gut breaking by hypercharged flux, and the other is the splitting of metacurves. So in both cases, interesting mathematics was required to understand this better, and in both cases there are open questions, which I would be very happy to discuss more than in the discussion session. So the status of these two ingredients, at first sight, both of these seem local. This is why they could be proposed already 5 years ago in these local approaches. However, on closer inspection, they do require understanding of the global details, which triggered a lot of formal progress, but which is still not 100% understood. So let us very briefly review these first three at least, so that we know the ingredients that then also Eran will be using for his elaborate SUSY breaking models. First, gut breaking. The idea is very simple. We have the gauge field strength, which we can expand into the 4-dimensional and the internal part, and if we give a VEV to certain components of the internal part, this will simply break the gauge group. So in other words, we switch on a non-trivial line bundle suitably embedded into SU5 on our gut brain. The embedding must be such that such that the generator, or such that the structure group of the line bundle is identified with the hypercharge U1 in SU5. Once we switch on such flux, also give a VEF to the corresponding curvature. The gauge group, of course, is broken to its commutant, which is SU3 times SU2 times U1y. The gauge bosons, the so-called XY gauge bosons, get massive, and if one does it right, one can also ensure that no scalars or no chiral superfields in those forbidden representations exist, and automatically then also the matter representations decompose corresponding to the decomposition into, into the standard model gauge group. And the nice thing about this mechanism is that it's topological. So unlike in field theoretic gut models, we do not have to consider actual Higgs fields and argue about dynamically gut-breaking potential. This is a dynamical gut-breaking mechanism that is simply part of our compactification data, if you like. And that's why it's very clean and people like it a lot. Second problem, now that we've broken the gut group, we can think about doublet triplet.
Have people tried in the past in hydraulic models with SU5 to play this game?
Yes, they have. The statement is that if you want, so as you know, one of the challenges is that you need to ensure that no Stückelberg mechanism makes this U1 massive. This is possible in type 2b or F theory because you can switch on fluxes which are not inherited from the ambient space. You could in principle do the same thing in heterotic, however, there you do not have the possibility of switching on fluxes not inherited from ambient space, and so you do get a Stückelberg mechanism. There is a catch to that. You could make sure that you get several U1s, say 2, such that you have one massless linear combination, which would then correspond to hypercharge. Models of this exist. For example, we had a model where you put the second line bundle into the second E8, say, then you have E7 times U1 and SU3 times SU2 times U1 from the first E8, and the linear combination then is hypercharge. That works. Only problem is that right-handed electron then would be charged under would have a slightly different charge assignment as would be required for gauge coupling unification. So gauge coupling unification is then a problem. However, ironically, as we know, gauge coupling unification is also at least affected to some way in F theory. So the situation might not be that much different at the end of the day. So yes, the group theory is the same. It's only really the localization in F theory that makes a difference here, and which forces us to play some other dirty tricks in heterotic. But of course, also as Laura pointed out, embedding line bundles into heterotic models is of course en vogue and offers a lot of new interesting possibilities.
What's the gut scale in this?
The gut scale is now so the gut scale as such is set by the volume of the force cycle, but the gut coupling, yes. So essentially the volume of the force cycle because you have a flux density of order 1, so flux numbers of order 1 on.
Because from a low energy perspective in 4 dimensions, it means that essentially above the gut scale you have decompactification.
Precisely, yes. So you never have a 4-dimensional gut. You have an 8-dimensional gut, if you like. You never have an yes.
So the
Yes.
gut scale
You never have a 4-dimensional gut.
decompactification scale. So
Yes. Or yes. I mean there is this slight hierarchy between the 10-dimensional and the 8-dimensional scale, but it's the 8-dimensional scale. Precisely. This was just since you asked, this was just these little considerations. Okay, so next typical topic, doublet triplet splitting is the question: how do we ensure that upon gut breaking, the doublet in our 5 Higgs remains massless, whereas the triplet becomes massive, and it must become very massive for reasons of proton decay, as we will see. So before looking at the doublet triplet splitting, let us first look at the matter, so the 10 and the 5 bar matter, which supposedly forms complete gut multiplets. So prior to gut breaking, if we only have
claims that you're
5 more minutes? Okay, I'll hurry up. Excellent. I almost have 1/3 of what I want to say. So prior to gut breaking, we start with, say, 3 generations of 10 and 5 by matter, and we do so by engineering gut universal gauge flux, so additional gauge flux which does not discriminate between the standard model particles which sit in the same gut multiplet. This is something, just another side remark, that was just proposed at the time in 2008, and a lot of work has been devoted to trying to understand what this gauge flux looks like in F theory. This is then this whole beautiful story of G4 fluxes, very complicated, but considerably better under control than in 2008. And we see that it's really needed. So this is really where lots of the technological developments went in. Put differently, prior to gut breaking, the 10 simply couples to some line bundle, some vector bundle possibly, but or some line bundle on our on our 10 curve, and its chiral index then is simply sensible to the first chain class of that line bundle, whatever it is, and which, as I said again, today we can describe very explicitly, at least for certain examples of such fluxes. After gut breaking, due to the different hypercharge assignments, the bundle is twisted, so the states now couple to this original bundle, tensor certain powers of the hypercharge line bundle, and by Riemann-Roch, then also the chiral indices are slightly changed by components of this hypercharge flux. So in order not to mess up the multiplicities of the states, we need to ensure that the hypercharge flux restricted to the 10 and also the 5 by matter curve must be 0. So this is a topological constraint. On the other hand, it also directly shows us what we have to do in order to accommodate for doublet-triplet splitting. Namely, there we do want the triplet to be absent, whereas the doublet should be present. Again, the same story applies as for the 5 by matter. So we need simply to make sure that there are no states coupling to the second power of Ly times the original gut universal flux. This ensures that there are no triplets. And then we need to make sure that there's one vector-like pair of Higgs up, Higgs down. This is just something that can be translated into a statement of the cohomologies of those line bundles on the curves into a mathematical statement, and then simply be treated. And if we have that, then by definition, we have no tree-level mu term. There are various ways to do that. A very simple, very clean, but also very difficult method, as it turns out, to do so is to ensure that the Higgs curve splits. Namely, suppose instead of just a single Higgs curve, we have two, a Higgs up and a Higgs down curve. Then, by exploiting here this logic, we can ensure that, that say on the Higgs up curve, this combination of flux gives 0 chirality, whereas this combination of flux, which counts the doublets, gives a +1, and on the down curve, everything with a minus sign. So we would have a pseudo-chiral Higgs sector, so to speak, Higgs up here and Higgs down there, something that can be computed just from these chiral indices along the Higgs up and down curves. This is a very beautiful mechanism. However, at the moment, this is not realized in global models. We do not yet know how to do that. What we know how to do is a lame version of that, where we do not split the Higgs up and Higgs down curves. In this case, the computation of these chiral, of the meta multiplets is slightly different, and essentially we need to turn on Wilson lines for the line bundle on the curves. So we could discuss this also more. But again, for considerably more technological input probably is needed to understand how to do this globally. So this is really worthwhile thinking about more. So doublet-triplet splitting. Proton decay, a last topic. We need to take care of dimension 4, dimension 5, and actually not dimension 6 proton decay. Dimension 4 proton decay would be due to operators, renormalizable operators of this type, which must be completely absent. And the necessary condition clearly is that 5 by matter and 5 Higgs are on different curves, because if they were on the same curves, then a wanted Yukawa coupling of this type implies also the presence of this unwanted one. So the curves must be split, but as it turns out, this is not sufficient. We'll come back to this in a second. Dimension 6 is not a problem, at least not in SUSY guts. Eran will talk about non-SUSY guts, where this might, and in fact is a constraint. And finally, dimension 5. These also have to be absent in SUSY guts. They come from effective non-renormalizable couplings of this type, which one gets typically by integrating out the up and down triplets. This is why they have to be massive. If they are, as they would be on the at the kk scale, one would get a suppression with 1 over mkk. There are certain other loop factors then that control also the proton decay, but this is not enough. So if indeed one has such a coupling between the Higgs, the triplet up and triplet down, then we typically do invoke dimension 5 proton decay, which would kill the model. The remedy is, like in field theory, a missing partner mechanism. We need to make sure that the triplet up and down do not couple. So in other words, the partner of the triplet up must be something else than the triplet down, which couples in here. So there must be kk terms of that type. And in that case, no integration to this dangerous coupling would be possible. So again, a necessary condition would be Higgs up and Higgs down at 2 separate curves. As we saw, this is also good because it prevents an order 1 mu term and realizes, it gives an easy way, at least locally, to realize doublet-triplet splitting. But again, this is only necessary, not sufficient. So the necessary picture would be to basically exploit the structure of these extra dimensions. We have our gut brain, and then the possibility to split the Higgs curve into 2, the 10 curve, and the 5 bar curve. So extra dimensions give us extra room, and therefore we can allocate things in such a way that everything that we don't want to be there is absent. This is basically the logic behind it. However, it's only a necessary condition. Curve split is not sufficient because, as was, I think, first pointed out by Watari, the local split of the metacurves may still give rise through the backdoor to these dangerous couplings. A sufficient criterion, however, as pointed out and studied then in great detail by Sakura and collaborators, is that we need extra selection rules that really ensure, in addition, absence of the couplings. And the easiest thing would be to have extra U1 selection rules which distinguish between the metacurves and forbid the certain couplings. For example, if we have an extra U1, like in a model SU5 times U1 with general charge assignments of that type, then we want the 10-5 for matter 5 by Higgs, we want the 10-10-5, but we don't want this dimension 4 and dimension 5 proton decay operators. And this then tells you, gives you relations between the charge assignments that you want. And in particular, if you want to forbid both of those, you need to ensure that Higgs up and Higgs down have different charges, and this is what Sakura et al. Then called this U1 Pachequin. So U1 symmetries are absolutely crucial for GATT model building, but there is a technical challenge. How do we understand those abelian symmetries? Abelian symmetries are not localized on the GATT brain. They are in the entire bulk, so this is something that can really, in a controlled manner, be understood only in global models. And indeed, this is where a lot of work went. It had been known since the original papers on F-theory that in order to engineer a U1, essentially we need a 2 form in our fibration, which is not in the base and not the volume of the fiber. Because by duality from M-theory, we can reduce the M-theory 3 form along such a 2 form then and get a U1. So we need a suitable new 2 form in our geometry that gives rise to a U1, which is, however, not just the Cartan U1 of an SU5. And in order to get new 2 forms, we need to place extra constraints on the complex structure on our 4-fold geometry. Technically, this means that our elliptic fibration must admit extra sections, so it must have a non-trivial model Y group. And indeed, there's been a lot of work trying to understand this from this geometric perspective. The first implementation of this effect in SU5 4-fold geometries was a very simple one, where simply the metacurve, the 5 curve splits into 5 matter and a 5 Higgs curve as a consequence of the appearance of this U1. And in addition, new metacurves arise away from the gut brain. One can on those extra metacurves, we have extra massless states, so we can view this as an unhiggsing of the U1, and on those extra massless states would then also be a candidate for right-handed neutrinos. And a lot of recent work has been devoted to understanding this in much more complicated scenarios and in great detail. Here's again our picture. So now we see that in addition to the matter on the gut brain, we have now an extra curve that goes away from the gut brain. This is what this should show. So this is non-local. Here we have extra singlets, right-handed neutrinos, and the extra 2 form essentially comes from this extra P1 in the fiber over this curve. So I don't want to discuss this now in even more detail, but just the message is that this necessary requirement from phenomenology can be translated into properties of the fibration. And I think the most complicated, so to speak, SU5 model is at the moment globally realized at an SU5 times U1 times U1 model. It can be realized as a certain toric hypersurface in a certain ambient space, just to demonstrate that these are not just words, but this can actually be computed. Here's one of the possible hypersurface equations. And we see that we can have various matter curves. We can have 110 with charge assignments of this type, various 5 curves, 3 of which would correspond to a matter in the standard model, 2 of which are then exotic. So we need to ensure that the fluxes are such that on those 2 curves we have no states whatsoever, but this is not a constraint on the geometry, but on the flux. And in addition, in these geometries, there are 6 extra singlet curves, one of which could then again play the role of the right-hand neutrinos. The others would be extra singlets. And in fact, this geometry was then analyzed from a model building perspective in greater detail by Sven and collaborators. And I think this shows nicely that really this investment into the geometry pays off in terms of phenomenological outcome. Okay, so having now basically reviewed the model building ingredients in F-theory, we can switch to the actual topic, namely supersymmetry breaking for such configurations. Yes?
How about a killer potential for method?
Yes, good question. I think it's fair to say that nobody really knows how to compute it. But the same is true. But the same is true already in type 2b, I would say. I mean, whenever you have a CFT, of course, you can make computations, but we discussed that also on Wednesday. Is it trustable to extrapolate those results from toroidal models to those complicated geometries? Probably yes, or hopefully yes, but I think it's fair to say that not only in F-theory does one not really have control. I mean, there are scaling arguments, of course, witty scalar arguments, but yeah. So let's leave it to that.
Okay. Thank you, Timo. Okay, so we are tight time, but unfortunately I cannot speak as quickly as Timo. Okay, good. So, having reviewed, having very kindly introduced all the important concepts for F-theory model building and reviewed some of the hard work that's going on in global model building, which in some sense, which is very important for understanding these things, I think I'm going to now discuss some ideas that come from local model building in F-theory, perhaps, and of course, the first question you might ask, what can the local model teach us about supersymmetry breaking, given that there is always a gravity mediation component to supersymmetry breaking, and a gravity mediation component will always depend on global properties of the manifold, and so how can we ever learn about supersymmetry breaking from a local perspective? I think I probably disagree with that criticism, because I think that there are 2 aspects to supersymmetry breaking and model building in string theory, from my viewpoint. The first question is, of course, how is supersymmetry broken? This is a very hard question, and something that, for example, something in large volume provides an answer for, but I think it's fair to say that this is a very hard question to answer in string theory in general. And the second question you might ask, same thing you might try and understand from supersymmetry breaking in string theory and model building is, once it is broken, what does it imply for the visible sector? And in some sense, this is actually an easier question to answer, I think, a more under control question. And I think the point is that due to this criticism, I think it's fair to say that one could put a line between these two and say that local models will not be able to tell us very much about this, at least not in a controllable way, but they may tell us about this. What does this supersymmetry break-in imply for the visible sector? And so I'm going to discuss this part. Okay, there are some, if you like, some kind of hybrid attempts at trying to understand supersymmetry break-in from a local perspective, but which are very nice, but I think it's fair to say that these are certainly not complete, because we know very well that the full properties of the vacuum must be understood before you can say supersymmetry is broken. So I'm going to concentrate on this part.
So when you ask yourself, when you say what you just said, you mean when you ask yourself how is supersymmetry broken in local model, you are thinking is equivalent to say that supersymmetry is broken in the open string sector.
No. So I don't say how supersymmetry is broken, but I will specify a mediator. So some field will get an F term, and then I will study what does this imply for the visible.
That I understand, but that I understand. No, I'm asking what you mean by saying that it's difficult to understand how supersymmetry is broken in local models. I guess as opposed to global models, right?
Well, it's not. It's probably easier to find some local models where supersymmetry is broken, but of course, one is not guaranteed that once you include the dynamics of the full spectrum of fields in the compactifications, they will not restore supersymmetry, because supersymmetry is a property of the vacuum. I mean, the classic example is, of course, KKLT. I mean, supersymmetry is broken before you include the Gaugino condensation, but then, of course, when you put that in, supersymmetry is restored. So one must understand the full vacuum. The basic idea of local theory model building is to consider an 8-dimensional gauge theory modeling the gut brane over this gut brane, and forget about the rest of the compactification. And the input for so-called semi-local model building is the gauge group and a Higgs background on this gut brane. So the gauge group and Higgs background tell you not just what the gauge group of the 4-dimensional gauge group, the AC5, but it also tells you this Higgs background. It tells you what are the matter representations of your model. This is what the geometry goes to, so matter representations and curves. And you can also turn on fluxes on the gut brane, and this will tell you things about the massless spectrum. So before I discuss them and supersymmetry breaking in them, I think it's fair to say there should be a word of warning about local models, which I want to mention. This is, as far as I understand it, the current status of semi-local model building in F-theory. Well, first of all, obtaining a realistic spectrum in these models is not a problem, in my opinion. One can get guts with double triple splitting and all kinds of nice physics. But of course, this may be due to the fact that we're ignoring many technicalities that appear once you actually try to do it properly in F-theory in a global model. So there are sets of models that can realize realistic flavor physics, proton decay, and many, many other things. I'm not going to review that here. As I say, the cutting-edge, most recent work, I think, is this. This is the most recent paper on this topic. So I will discuss instead issues relevant to supersymmetry breaking, but first a remark on this program of local model building in F-theory. So first of all, there is a general constraint that was found for local models spectra coming from hypercharged flux gut breaking, and that is if you have a U1 Pechi-Quinn, then doublet triple splitting automatically implies that you have some exotics in the spectrum. This is sort of a general result, it seems. And it turns out that this statement is actually can be understood as the cancellation of certain anomalies involving the standard model gauge groups and also the hypercharge with an additional U1 symmetry that you automatically have. So let's say, for example, this U1 Pechi-Quinn. And it turns out that because the hypercharge cannot induce, at least we thought probably it cannot induce anomalies in the spectrum because it's globally trivial, these anomalies must, well, not vanish, but they must satisfy certain properties. They must not change by the introduction of the hypercharge flux. And this turns out to imply this theorem. However, later it was realized, much later after a number of years of semi-local model building, that actually there is a constraint that has been missed, and that is that there is also this anomaly which involves hypercharged flux in U1s. It's a slightly strange anomaly because before the gut breaking, it's an SU5 U1 anomaly, which of course vanishes automatically because it's a non-abelian gut group. But after the gut breaking, after the hypercharged flux breaking, this can potentially be non-vanishing. And it turns out actually it's non-vanishing in many of these models. In fact, as far as I understand, it's basically non-vanishing in all the local models that have been constructed in the literature. And by this reasoning that hypercharged flux should not induce any new anomalies, since this anomaly is induced precisely by the hypercharged flux, since without it it's an SU5 times U1 anomaly and it vanishes, these two reasonings would imply that any local model which has this anomaly in it is somehow inconsistent. And since actually it turns out that all the local models had this anomaly, it's bad news. Okay, so well, there are potential ways out of this issue. First is that in type 2b string theory, it turns out that hypercharged flux can induce anomalies in the spectrum, which are then cancelled by the Green-Schwarz mechanism and still remain massless. And this is due to subtlety with the fact that, in fact, the hypercharged flux need not be globally trivial, as somehow stated, at least in F theory, certainly in 2b it need not be, but rather it must be globally trivial with respect to the orientifold even sector, and it can couple to the orientifold odd sector, closing sector in type 2b, and the orientifold odd sector in type 2b has its own Green-Schwarz anomaly cancellation mechanism, and it can cancel the anomalies associated with hypercharge. However, the analogous mechanism F theory is certainly not understood, so perhaps if we can understand how this can work in F theory, we may be able to solve this problem. So this is certainly a way out, I think. Another possible way out is that actually more models are possible in global constructions than in the local reasoning. I think this is somehow a surprise that we've learned from global model building. Of course, one would expect constraints when you look at a global model compared to a local one, but it's somehow surprising that when we studied local ones, we found out that actually we were not being the most as general as we should have been when studying the local models. There were more options available.
But surprise. I mean, we know that in the type 2b at singularities, people have been working for 10 years to find just some model. I mean, we know from the type 2b side that doing local models is it's very, very hard to find something. But globally, it's quite easy in all kinds of other constructions. So why should it be a surprise in F theory?
Well, I think the analog of this, let's say if you were thinking about type 2b brains of singularities, would be that we found some global model, Calabi-Yau, which had some singularity in it that we never thought about when thinking about the local singularity. I think that would be surprising, in my opinion. This is the analog statement here. So in some sense, we found global models that had more local models in them than we thought about when we were thinking just about local models. I found that surprising. Okay, anyway. So this means more possibilities than have actually been studied in literature, and this may help us get around this problem as well. So just hints for possibility of avoiding this problem I just discussed. No concrete realizations yet, but maybe there's a way out. So with this caveat in mind, we'll return to supersymmetry breaking in semi-local model building. So spectrum of fields in these models come from the adjoint to V8. So what do we have? We have singlets, we have 5s, and we have 10s. And as I said from my philosophy slide at the beginning, I'm going to assume an F term for some field, in this case a singlet, or what these people did when they studied it, didn't assume that, but they used an F term for a singlet and explored the consequences for the soft terms in a visible sector within these local models. So the initial studies were using gauge mediation with complete gut multiplet messengers. So here you have this coupling in your theory, and you just say this singlet, I don't know how, but you can find some models, gets an F term, and then you say, what does this imply for the soft terms? So actually, most of these models utilize a U1 Pechi-Quinn. So a symmetry, U1 symmetry that the Higgses have different charges under, and because that solves the mu problem for you, I mean it explains, solves the mu problem, and it also solves the gauge mediation mu b mu problem, which is to explain why this scalar potential operator should be suppressed compared to this one. You have to try and suppress this one compared to this one, because they both arise at one loop, and they have different dimensionalities, which means that if they were had the same coefficients in front of them, you would naturally either get the b mu term or too big or the mu term too small. That's the mu term of gauge mediation. So U1 Pechi-Quinn will help you with that, because it will forbid this operator for you, because this will not be vector-like, the Higgs have vector. And because, as I said before, such a U1 Petriquin implies non-gut exotics, it's then natural to consider not this, but a more general thing, since you use a U1 Petriquin, and if you study how you find that actually there are non-gut exotics in your theory, use them as mediators instead. So this is some kind of gauge mediation with messengers that are not complete gut multiplets. And I think this is quite nice, because if you study this, then you find an interplay between the fluxes and the spectrum in your theory and the soft terms that you get from supersymmetry breaking. So this is an example. So this is the spectrum of fields that you have in your theory. These integers are the fluxes that you may turn on. And then for some particular choice of fluxes, you find some particular pattern of soft masses. And if you chose some other form of fluxes, some other spectrum, you would find some other soft masses. So this is an explicit connection, which I think is something we should strive for in string theory, which is connects things like the spectrum of fields to the soft terms. Something that's, I think, is hard to, anyway. And one further deformation of this idea of gauge mediation is the so-called U1 Petriquin deformed gauge mediation. And the idea there is that this U1, it becomes massive. It's massive at a string scale, so you integrate it out. And as I said, it can generate, and one of the things that it can do is it can generate for you a coupling between the field that gets an F term and the visible sector fields. So through this kind of diagram, for example. So these are charged into the U1s, but also the visible sector fields are charged into U1s with some particular charges. And when you integrate this out, you get this operator, and this gives you a soft mass of this form. And again, this is a nice connection, I think, between model building properties and the soft terms, because the charge of these fields under this U1 will determine the size of this soft term. So here is again some soft term spectrum, which I will not explain in detail, but some soft term spectrum. And the only thing is that I don't think, well, you probably cannot see it very well, but I think the red lines are the soft terms as if you would calculate without this contribution of this to soft terms, and the red lines and the blue lines are ones with the contribution from this thing. So you see that the soft terms get shifted, and they get shifted in a model-dependent way according to the charges of the visible sector. So again, a connection between model building and the soft term patterns. I think that's quite nice.
These spectra are completely constrained, if I understand. They depend on one parameter.
So they depend on?
Like, for instance, would you be able to do split SUSY with this kind of model?
I think so, yeah. There's not, this, I would not take the spectrum so seriously. I think these are kind of essentially to illustrate the ideas. I mean, the only thing I wanted to illustrate by showing this is that the soft masses get shifted according to the charges of the fields under an additional U1 symmetry. And that's the main point of this thing. I mean, to actually lift all of this up and down, you can do that by tuning picking some other parameters in your model, like the size of this F term, of course. I think you can also generate fermion diagrams here for this thing. It affects all of them.
Well, the thing is that it seems to me that the same quantity controls both the universal gaugino masses and the universal scalar masses.
Well, I guess that's the property of gauge mediation generally. Does not. I mean, this is gauge mediation, so yes. I mean, yeah. Okay. I mean, definitely.
Actually, this is equivalent to having some difference, actually.
Sorry? This?
I think this is equivalent, integrating out the automatic equivalent before integrating, having some difference from the U1. So I don't think we generate gauge masses. I think we generate only scalars, as far as I know.
Okay, but the gaugino masses are just generated through the usual gauge mediation mechanism at one loop, so...
But it's a different parameter.
Yeah, that's why I've said there's more parameters in the model. This is just to illustrate this particular contribution to the soft masses. There's other contributions which are the usual gauge mediation contributions. So, okay. So I think something that's interesting that string theory can tell us that I think is hard to answer from a four-dimensional perspective are flavor changing effects. And the nice thing about this, for example, the U1 Petriquin soft terms and other gauge mediation things, is that they lead to this U1 Petriquin in particular, it leads to no off-diagonal soft terms. So it helps with flavor change neutral current. However, since this mediated by a massive U1, this U1 is at the string scale, so it's essentially a gravity-mediated contribution. And it's not clear. The problem with gravity mediation, of course, is that it's not clear. Even if at the tree level you find some nice flavor structure, it's not clear why this should persist once you include other modes that lie at the gravity scale. That's the problem with gravity mediation and flavor changing currents. And one could then needs to do calculation, and one can calculate, for example, just an example of one thing that's been done is calculate corrections to this scenario from other heavy modes in your theory, which are no lighter than this U1 that's also at the string scale. So there's other string scale modes in your theory. And when you calculate the diagrams from them to the same operator, so before it was XX dagger, QQ dagger, now it's XQ, XQ, with some other massive mode mediators here, you find that you can do this calculation you find that this contribution is associated to some wave function overlap calculation, and you can do it, and then you can show that soft terms from these operators are diagonal but not degenerate. And if they're not degenerate, that means that they will lead to flavor change in neutral current constraints upon going to the mass basis. So I think this is something to be careful. I think this was a criticism of these models at the time, that of course you may call it gauge mediation, but if your soft terms are being generated by something that's at a gravity scale, then essentially you suffer from all the usual problems of gravity mediation. Some brief remark, I put this on the some other work that's been done. I think I put this in the local picture in the sense that I think it's kind of a local approach to gravity mediated supersymmetry break-in, in the sense that one essentially guesses the mathematics for the fields in the model, and then specifies. I mean, this will be for toroidal models. We have some calculations for the matter field modular weight, and then you just say this thing persists up to some corrections from flux for F theory, and then you just assume that some modulus gets an F term without specifying what the mechanism is. So that's why I call this a kind of local. It's from the same philosophy. So you assume that this Kähler modulus gets an F term, and just some work that's been done is looking at the pattern of soft masses that you get from this assumption. I think, I guess one thing just to highlight is that it turns out that this pattern of soft masses is precisely the one that you get naturally for heavy Higgs. So just very quickly, this is the Higgs mass in the MSSM, and to get a heavy Higgs, you essentially want this xt to be as big as possible. You want this contribution. So this is essentially the maximized for xt being, well, not as possible, maximized for xt being the square root of 6 of the stop mass. And it turns out that in these models, with these Kähler metrics, and just for an F term for the Kähler modulus, you naturally get this kind of thing. So for example, A over M is around 2. So this is, and you're at large time beta, so this term kind of doesn't dominate. So you have A over M. And this being 2 is roughly square root of 6, so I mean, it's roughly around the region that you naturally get a heavy Higgs. So this was the kind of something I think that's quite nice, it's been pointed out in these papers. So let me just talk about some other calculations that are done. I think something that's important, which is calculations to do with flavor changing currents associated to gravity-mediated contributions. Okay, this is just to do with the previous slide, that a possible lesson is that minimal supersymmetry models are becoming very hard to accommodate in parameter space by HT data, and it may be that string theory has an opportunity there to motivate a particular small region of parameter space that's been left over. That's from the past slides. And if one does a more detailed analysis of soft terms, actually, this is, I think, quite nice work that was done by these people, is that, so for example, soft terms are mediated by this no-scale break-in, which can associate to the flux breaking. And of course, what is usually done is some 4-dimensional supergravity analysis. But since it's gravity mediation, one should really probably study some kind of an 10-dimensional analysis of this soft terms. And what that means is that one should account for effects where these fluxes actually vary. The density of the flux can vary over the Calabi-Yau space or over the gut brane. Whereas in 4-dimensional perspective, it's just taken to always be a constant. Actually, it can vary. This is the analog of including alpha prime corrections to the 4-dimensional analysis, actually, because you're looking at higher modes. And when you do that, you find that you get corrections to the 4-dimensional analysis results. And these corrections, well, first thing, they generally induce flavor changing currents, which is just what you generally expect from gravity mediation. And the corrections that is induced to the four-dimensional result are not that suppressed. I mean, so for example, from the variation of the flux over the Calabi-Yau, you find a suppression to the four-dimensional result, if you like, of m gut over m Planck to the third, which is not that small. And the corrections from variation of the flux over the gut brane correct the results that you expect by alpha gut to the half. So that's again not that small. These are like big corrections. So so large corrections to precision physics associated with change of neutral currents. And when you take these into account, you have to push the spectrum up in order to meet the constraints to around the 10 TeV scale at least. So I think that's important. Although actually with the current LHC results, constraints from FC and Cs are becoming less important because it's actually the fact that we've not seen any colored particles is really pushing the spectrum up the most, more than favor change neutral currents. But it's still an important thing to think about. Okay. General lessons, pattern softmatter is sensitive to wave function details. Okay, so since the heavy TV spectrum is already quite tuned, some people have been thinking, forget about naturalness, maybe it's not a good guide, and let's think about non-supersymmetric models. So models of high-scale SUSY break-in, in this particular case, 10 to the 10 GeV, the scale is motivated by the vanishing of the Higgs self-coupling in a standard model when you run it up. And people study essentially supersymmetry breaking scale induced by flux. The point is that this scale is naturally actually the scale you would expect by a string scale flux supersymmetry break-in without any further questions. So let me just brief very quickly. Consider this, essentially have such a supersymmetry break scale in the middle of your running here, then one would expect gauge coupling equation to get ruined. But then these people say, okay, that's okay, because we know the gauge coupling doesn't really work in may not work in F theory. These are corrections that are there. They actually don't have to be there. This is some work that we did. The gauge coupling can work precision gauge coupling can work just fine in F theory, but it can also be broken. And actually, you can put this together with the shifting in the gauge couplings by the supersymmetry breaking scale, which is the intermediate scale, and actually the two fit together well. So you see there's this picture here, and then supersymmetry is broken at this high scale, and they change the running, and the running here is not the usual gauge coupling unification, but actually it matches precisely what you get from these corrections for F theory. So that's something else. Just very quickly, the problem is that in these models, the gut scale, because the gauge coupling configuration changes, is actually lower. It's 10 to the 14 GeV, and then you have problems with dimension 6 photon decay. And so one way to avoid that is to localize the gauge mediators that induce this decay using flux away from the curves where the things live, where the matter lives. Okay, that's it. So Timo has, sorry, very, very quickly.
Thanks very much, Aaron. So it would, of course, be ridiculous to talk about realistic model building string theory without at least touching upon heterotic string theory, which we all know was the first approach to string phenomenology and is still producing fantastic results. In particular, heterotic orbifolds were among the first approaches to getting nice models from string theory. And these can, of course, be viewed as a special limit of heterotic compactification of smooth Calabi-Yaus with stable vector bundles. Essentially, you think of both the curvature of the Calabi-Yau and the curvature of the gauge bundle localized at the orbifold fixed points. So this said, this is my excuse for not covering heterotic on smooth Calabi-Yaus, even though this is a beautiful topic which I'd love to talk about with lots of recent progress. But Lara at least touched upon certain aspects of those, even though not the model building aspect. So I think since this topic would otherwise be underrepresented, it's fair to discuss a little bit about the heterotic orbifolds instead. So the nice thing about those, of course, is that one has an explicit conformal field theory realization and therefore can, at least in principle, do coupling computations explicitly. As you know, in order to define such a model, one needs to choose and define the boundary conditions for the left-right moving sectors with the help of, first of all, the defining data of the torus. These are the torus translation vectors. Then we choose a certain orbifold group, let's say a Zn group for simplicity. And indeed, one also has to define the embedding of the right moving gauge sector via Wilson lines and gauge twists. And in these models, just as in type 2b, in fact, one does get a hierarchy of localization of states. So there are two types of sectors. There's the untwisted sector, where the corresponding string fields are unchanged with respect to the group by which we divide. These give rise to bulk modes, which in this case propagate on the entire torus, whereas in the twisted sector we get states localized either at fixed points or fixed planes. So while the typical prejudice is that heterotic string theory is global in the sense that everything propagates in the bulk, there are indeed very well-defined sectors, something propagating on the entire torus, something propagating at fixed planes, and something stuck at fixed points. And this is, I think, also the logic behind the success of those models, because like in type 2b in F theory, we can now play with these various localization hierarchies to put things in such a way that it works out fine. And we'll see how this works. And by the way, the same is true also in heterotic on Calabi-Yau. For example, if we have elliptically fibered Calabi-Yau three-folds and spectral cover bundles on those, then also the meta curves localize, the meta states localize on certain curves in the base. So again, of course, by duality, this must all be related, but localization of gauge degrees of freedom versus matter degrees of freedom is really key to getting Qt phenomenology out of it. So one of the models that was particularly successful and has been studied in the past, starting with this model, I think there were more references prior to that. Please consult those papers for the original ones, is T6 over Z6 primed, where one has a Z2 and a Z3 subgroup acting in this fashion. So for example, the third torus is left invariant so that by the Z3 subgroup, so that one gets these fixed planes essentially, and one has corresponding Z2 fixed planes, the second torus at these 4 times 4 points, and then one has also the complete fixed points, 12 of those, where then the twisted states are localized. And a lot of model building has been done. Something like a mini landscape of close to or realistic models was produced by a large number of authors. This is really just a small number of names. Let's very quickly review one of the benchmark models, what these authors call the benchmark model on T6 over Z6 primed. It has gauge group SU3 times SU2 times U1Y. On the one hand, then in the hidden E8 we have an SU4 times SU2, and in addition we have 8 extra U1s, one of which is anomalous. The Higgs fields, Higgs up and Higgs down, are such that they propagate in the bulk, so these are modes from the untwisted sector. The doublet-triplet splitting is realized in those models through a clever choice of Wilson lines. And the fact that the Higgses propagate in the bulk is important to get the Yukawa couplings in a suitable fashion, as we will see in a second. The first two families of matter localize at fixed points, the actual fixed points. They transform in a complete 16 representation of spin 10. So we have here, again, similar to F theory, this so-called local gut picture that at certain points in codimension, the gauge group, quote unquote, is enhanced so that we have states transforming in full representations of that gauge group. It's slightly different to F theory. In F theory, we would have the adjoint, from which we get now the extra states, and here we have actual representations like the spin 16 representation, the 16 representation of the spin 10 group. But the logic is very similar. And the third family, the heavy family, is a patchwork family, as they call it. So it's partially in the bulk and partially at fixed points and fixed planes. And the overlap structure of now the Higgs, which is in the bulk, with the, say, the top, which is also in the bulk, can explain why the top is very heavy, while other families, in particular the first two, which are at these fixed points, are not so heavy. So again, this also is very similar to what Iran just discussed. Wave function localization essentially in the extra dimensions can be accommodated in a suitable fashion to get nice hierarchies and patterns of couplings. In addition, all those models have extra vector-like states, a huge number of them. However, it is argued that these can be decoupled by giving suitable VEFs to, say, charged singlets. This is, of course, one of the key things to be checked, but this is the logic in this approach.
Singlet moduli?
Exactly, singlet moduli, yes, I'll come to those. So both charged singlets and exotic states, vector-like, so Stern model charged, and yes, both need to decouple. So now to the SUSY breaking. Of course, SUSY breaking requires first moduli stabilization. The moduli in the game here are a small number of untwisted complex structure moduli, a small number of untwisted Kähler moduli, and in addition we have typically order 100 charge vector-like singlets. These are these charge singlets at the twisted sectors, which Massimo was referring to. These would be the analog of the bundle moduli in the heterotic string, which Lara discussed in great detail in her nice talk. And of course, we have the dilaton. So, which are possible sources of potentials for moduli stabilization? First of all, we have a perturbative superpotential, which depends on the charge singlets and the complex structure moduli. And again, we've seen that before. This is the precise analog of the Chern-Simons superpotential on smooth Calabi-Yau threefolds, and its stable points correspond to the solutions to the f0,2 equals 0 condition in the Hermitian-Yang-Mills equation. So the way it is formulated in these papers is simply compute now order by order different superpotential terms, couplings between the singlets and the complex structure moduli. This is something that in principle can be computed in a CFT, which is very nice. Of course, at some stage the computation has to stop because you can have only finite power of computation. You can do this order by order, but this superpotential is just the expansion of this Chern-Simons superpotential. So the pro is you can compute it in CFT. The disadvantage is you have to stop that computation at some stage, and unlike in the heterotic string, you do not have, at least not as clearly, such a sexy interpretation in terms of the geometry of those gauge bundles. So Lara explained to us how one can, even without doing this computation of the superpotential explicitly, infer the stable points by looking at this combined moduli space of open string moduli, of vector bundle moduli, same thing for vector bundle moduli and complex structure moduli. Here we don't have this picture, but instead look at the expanded version of that superpotential. And the logic is that all the terms that are allowed by string deselection rules should be present and are present with order 1. This is an assumption. To really pin it down, one would have to compute it, but at least the first assumption is certainly reasonable. So these are the F terms. In addition, we have, of course, D terms. In particular, there is one anomalous U1. So we have D terms that involve both the singlet fields and also all the visible fields, and the Phi-Etilopoulos term, if present, for this one anomalous U1, which depends on the dilaton. Third, we have possibility of gaugino condensation. So if the hidden gauge group is confining, then there is a certain scale at which then the gauginos can get a VEV, and in the effective theory, of course, we can write this as a non-perturbative superpotential of that type, where the prefactor, what one would call the Pfaffian type 2B language, depends on the bundle moduli or the brain moduli, i.e. the charge singlets, and the complex structure moduli. And finally, in smooth heterotic, one could also consider worldsheet instantons, which would depend on the Kähler moduli. This is not possible on the T6 because those worldsheet instantons have too many zero modes, would not correspond to the superpotential. They would correspond to Beasley-Witten type terms, but they are not present here. So, but the upshot is the ingredients for moduli stabilization are really like in heterotic on smooth Calabi-Yaus. The only thing that is missing is flux, three-form flux, for the reasons discussed, or at least is more constrained. So we would have to go to non-Kähler spaces and have problems with this. This was discussed extensively on Wednesday, I think. So with these ingredients, people could either try a two-step approach, so mimicking kind of this KKLT approach. The logic is that if we work in global supersymmetry, then typically the perturbative superpotential and the D terms fix all complex structure moduli and charge singlets in a supersymmetric fashion with W0 equals 0. So this is the typical assumption, which can be, which can at varying level of detail in the literature be made more concrete. But if we start from this, then we can take this as the first step a la KKLT, and then in the second step, after integrating out the charge singlets and the complex structure moduli, look at the gaugino condensate, which would fix the dilaton and also break supersymmetry and uplift. This is at least the logic that one could envisage. Of course, there is a challenge. The challenge is to avoid the obvious runaway direction for the dilaton as to infinity. And in order to do this, there are three ways discussed in the literature. Originally, people were thinking of possible non-perturbative corrections to the Kähler potential, which could do the job, but this has to be justified quantitatively. I mean, non-perturbative computation of Kähler potential is difficult. There are constraints for what the Kähler potential can look like by modular invariance, etc. But make this concrete from my understanding is hard. One could consider a racetrack potential, so two such non-perturbative effects to balance them. Only problem is that in some of these particularly beautiful orbifold models with nice visible sector, one oftentimes doesn't have two condensing gauge groups but just one. So then just by inspection this option is not there. Or third, you could use an interplay of the gaugino condensate and other SUSY breaking or uplifting matter superpotentials. Also something similar, or yes, actually similar in logic to what we heard yesterday for the uplifting. For example, in this paper, people looked at a Poloni type model. So they simply assumed that there is a superpotential of that type. Of course, the challenge is you must really argue that all those terms exist and that they exist at the scale and that there are no runaway directions. So yes, please, Emilia.
If this one is anomalous, it is too naive.
I fully agree. I fully agree. I'm just reviewing this to give you an overview of what people of what people do. So okay, so this would be an extra point, but even beyond that, one has to argue that one has a W0, that it's small, non-zero. As we heard, fluxes do that in type 2b, but it's not so clear what the role of that is in heterotic. We would have to argue also for the origin of mu here, would have to be small typically, suppressed. So in string theory it will of course be field dependent, but then we have to take into account the field on which it depends, and essentially we would have to stabilize the entire superpotential all at once. This would probably be safer. This would be approach 2. This was studied for certain ansatzes, I would say, in this paper, but again the challenge is all terms must be computed and stabilization must be shown before one can claim victory. So in any case, so this is the package, I think, of tools that people have in mind, and then one can assume that this works out and try to find certain patterns then for the SUSY spectrum. Just for definiteness, let me stay in this framework of this Poloni type model with a certain assumed Kähler potential. Then the authors argue that one can find parameters, which in fact are to be computed. One can find parameters where there exists a SUSY breaking vacuum with all fields of order 1. And they also argue then that the F term of the dilaton is suppressed with respect to the F term of this Poloni field by a factor of 1 over the log of m Planck over m3 half, which is just observed to be just like a one loop suppression, order 4 pi squared. And as a result, they show that for example, for the gaugino masses, the gravity mediated and which is suppressed and the anomaly mediation terms compete. So this is their main conclusion, and they claim that this is also more general and does not depend on those assumptions.
When you say what I wanted to say, if you are anomalous, you cannot have pure gaugino condensation like this for all the gauge invariance.
Yes.
The fields in the
Yes.
you need fields in the hidden sector which are charged, and therefore you need something like
Yes.
QCD or something.
Yes. Yes. I fully agree. That said, if one had if one has such a spectrum, if one has such a suppression of the gravity versus the gauge mediation, versus the anomaly mediation, no. If one has this interplay of gravity mediation and anomaly mediation due to this suppression of the gravity mediation contribution to the gaugino soft masses, one gets this pattern, which is called mirage pattern, due to this, due to the fact that the gauginos then would unify at some intermediate scale before they diverge again or part again at lower energies. And one sees, for example, for fields like this that are localized in the bulk, one has a similar spectrum. So here now again, the different soft masses will depend on the different degree of localization. Okay, so just to state that what seems to be done in this field. And finally, very quickly, type 2A model building. This is just the sister of type 2B and F theory. We have, instead of type 7 branes, of course, intersecting to 6 branes with chiral matter at the intersection points. In the perturbative limit, just as in type 2B, due to extra perturbative selection rules, non-GART approaches are favored, so either Paty-Salam or models or direct standard model constructions. This has been studied in great detail on toroidal orientifolds. I think one of the best models, again, is a T6 over Z6 by Gabriele, and further study then also in this paper. Extension to smooth Calabi-Yau is interesting but challenging because finding special Lagrangians on Calabi-Yaus is difficult. Moduli stabilization in type 2A wasn't discussed much, but we did mention already in this conference that Ramon fluxes can in principle stabilize all moduli. The question is, how severe is the back reaction compared to type 2B? And in addition, possible sources for SUSY breaking uplifting terms include instantons or Gay-Gino condensation, and this is something that was used in great detail in M-theory on G2 inspired model building, where in particular it was certain racetrack superpotentials are able to stabilize all moduli. But this is in a G2 inspired supergravity approach, I think, and it would be very interesting to make this more concrete in actual compactification. So just final remarks very quickly. The SUSY breaking in realistic models clearly is the holy grail of string pheno, what we all are hunting after. There's a local approach without specifying the source of SUSY breaking. There's a global approach where we try to be more explicit, which is different, realized in different corners at a varying level of detail. I think both the SUSY breaking and the moduli and the model building technology call for further investigations in the future. And particular, once again, there's been a lot of recent technical progress in model building, for example, in F theory and in moduli stabilization and heterodic. And both of these are necessarily very mathematical. So the math is here really at work for phenomenology. And this is not just lip service, but we need all those structures in order to say something about the physics. Be that as it may, I think it's fair to say that string theory is in very good shape with or without supersymmetry, because if supersymmetry is not found at the LHC, then we have an actual framework to study things like the weak hierarchy problem. We have an actual theory to study, and I think we have every reason to look forward to a very bright future. So, see you.